Hello everybody, let's continue topic about total station and Theodolites. Lesson 10. Particularly geometry of the theodolite and total station. So here you can see a vertical axis of the theodolite goes up through the center of spindles and is oriented over a specific point on the Earth's surface. The circle, assembly and alidate revolve about this axis. The horizontal axis of the telescope is perpendicular to the vertical axis, and the telescope and vertical circle revolve about it. The line of sight, also you can say a line of collimation, is a line joining the intersection of the reticle crosshair and center of the objective lens. The line of sight is perpendicular to the horizontal axis and should be truly horizontal when the telescope level bubble, if of course there is one, is centered, and when the vertical circle is set at 90 degrees or 270 degrees or 0 for vernier transits. This figure shows the geometric figure of theodolites and total station. The most important relationships are as follows. The axis of the plate bevel should be in a plane perpendicular to the vertical axis. The vertical crosshair should be perpendicular to the horizontal axis. The line of sight should be perpendicular to the horizontal axis. Horizontal axis should be perpendicular to the vertical axis, standard adjustment. And in addition, the vertical circle should read 90 degrees when the telescope is level. So, about objective lens. Telescope include objective lens, and telescope, this is a focusing instrument that consists of an object piece and an eyepiece at opposite ends. It's rotated around the horizontal axis in vertical plane. About alidate. Alidate is used to align the telescope with the target. Leveling screw is used to ensure the theodolite is on a leveled plane. Electronic display displays the angle reduced and also eliminates the uncertainty associated with a reading manual scale. 3D bus allows the theodolite to be mounted on a tripod. Optical plumb is used to center the theodolite over a fixed point. Here you can see a scheme of theodolite telescope. This is objective, internal focus lens, focusing drawer, a reticle and crosshair, erector, eyepiece drawer, and a magnifier. And this is a diagram of a telescope optical system. Let's talk about line of sight collimation correction. Testing and adjustment procedure is described on the following steps, and the vertical line of sight should be perpendicular to the horizontal. Horizontal axis, so that a vertical plane is formed by the complete revolution of the telescope on its axis. So, set up the instrument at point A. Take a backside on any well-defined point B. Transit the telescope and set at point C on the opposite C1 on the opposite side of the theodolite, 300 feet away, at roughly the same elevation as the instrument station. After that, loosening the upper or lower horizontal plate clamp, and with the telescope still inverted from step 3. Sight point B again. After sighting of point B, transit the telescope and sight in the direction of the previously set point C1. It is highly probable that the line of sight will not fall precisely on point C1. So set a new point C2 adjacent to point C1. With a steel tape, measure between C1 and C2 and set point C, midway between them. Point C will be the correct point, and this sixth step also describes double centering, a surveying technique of producing a straight line. Also, you can see on next section about horizontal crosshair adjustment. It must be adjusted so that it lies on the optical axis of the telescope. To test this relationship, set up the instrument at point A and place two stakes B and C in a straight line B about 25 feet away and C about 30 feet away from point A, with the vertical motion clamped. Take a reading first on C, K, and then B, G. Transit the telescope and set the horizontal crosshair on the previous rod reading G at B, and then take a reading at point C, K. If the theodolite is in perfect adjustment, the two rod readings at C will be the same. If the crosshair is out of adjustment, the rod reading at C will be at some reading L instead of K. To adjust the crosshair reticle up or down by first loosening and then tightening the appropriate opposing capstan screw until the crosshair lines up with the average of the two reading M. Angles measured with a direction theodolite. This is an example of field notes for directions. How to measure it? Case 1. A laying of angles. The angle is to be laid out no more precisely than the least count of the theodolite or total station. Assume that you must complete a route survey where a deflection angle has been determined from aerial photos to position the center line clear of natural obstruction. So the surveyor set the instrument at the point of intersection of the tangents and then sights the backline with the telescope reversed and the horizontal circle set to 0. Next, the surveyor transits the telescope, turns off the required deflection angle, and sets up a point of line. So the deflection angle and a point is set at C1. Then the surveyor loosens the lever motion and repeating instrument sight again at the back line, transits the telescope and turns off the required value. It's very likely that this line of sight will not precisely match the first sighting at C1 if the line doesn't cross C1 and you mark a C2 is made and the instrument operator gives a sighting on the correct point C, which is midway between C1 and C2. So process look angle, rotate theodolites, then open look and measure again the same angle and should have double the first angle measurement. Prolonging a straight line, also known as double centering, is a common survey procedure used every time a straight line must be prolonged. The best example of these requirements is in route surveying, where straight lines are routinely prolonged over long distance and often over very difficult terrain. The technique of reversion is used to ensure that the straight line is prolonged properly. So in figure, the straight line AB is to be prolonged to C with the instrument at B. Sight is made carefully on station A. The telescope is transited and temporary point is set a C1. The theodolite is revolved back to station A. The telescope is in position reversed to the original setting and a new sighting is made. The telescope is transited and temporary mark is made C2 and adjacent to C. So repeat, start by taking distance at A, then go to B, rotate 180 degrees, look back at A, plunge and make another line towards C. Backing in or interlining. It's sometimes necessary to establish a straight line between 2 points that themselves are not indivisible. That is, a theodolite or total station set up at one point cannot, because of interviewing field beside it at the another required point. It is usually possible to find an intermediate position from which both points can be seen. You can see that point A and B are not invisible, but point C is in an area from which both A and B can be seen. The bucking procedure is as follows. The instrument set up in the area of C and as close to the line AB as is possible to estimate. The instrument is roughly leveled and a sight is taken on point A. Then the telescope is transited and sight is taken toward B. The line of sight will of course not be on B but on point B1 or B2, some distance away. Nothing roughly the distance B1B and the position of instrument between A and B. Halfway on or 1/3 or 1/4 of the distance AB. The surveyor estimates proportionally how far the instrument is to be moved to be on the line AB. So instrument is once again roughly leveled position C2. So part here Theodolite approximately, and the sighting procedure is repeated. This trial and error technique is repeated until after sighting A, the transited line of sight falls on point B or close enough to point B, so that it can be set precisely by shifting the theodolite on the leveling head shifting plate. When the line has been established, a point is set on point C, that the position can be saved for future use. This procedure of bucking in can be accomplished in a surprisingly short period of time. This is you can see elevation and top view, yes? So read A, then plunk to B. If distance between B and B1 is 1 meter, then you have to move 0.5 meter to find C, then to the sighting again. Intersection of two straight lines. Intersection of two straight lines is also a very common survey operation. With the instrument set on Main Street station and a site taken also on the Main Street, 2.24 feet are established on the Main Street, 1 point on either side of where the surveyor estimates that the Second Avenue will intersect. The instrument is then moved to a Second Avenue station and site is taken some distance away on the far side of the Main Street. the surveyor can stretch a plumb bob string over the 2 points established on the main street. And the instrument operator can note when on the string the second avenue intersect. So put two strings between point and then get the intersection. In route surveying, obstacles such as a river or chasms must be traversed. In figure, the distance from point A to the station established on the far side of the river can be determined by solving the constructed triangle or triangulation. The ideal triangle is one with angle close to 60 degrees. Also, angles as small as 20 degrees may be acceptable. Rushed terrain and heavy tree cover adjacent to the river often result in a less than optimal geometric figure. The baseline and a minimum of two angles are measured so that the missing distance can be calculated. The third angle should also be measured to check for mistakes and to reduce errors. If you see this figure, the line must be prolonged past n obstacles, a large 3. In this case, a triangle is constructed with the 3 angle and 2 distance measured. As we noted earlier, the closer the constructed triangle is to equilateral, the stronger is the calculated distance BD. Also, the optimal equilateral figure cannot always be constructed due to topographic constraints. And angles as small as 20 degrees are acceptable for many surveys. In property surveying, obstacles such as trees often block the path of survey. So, in route surveying, it's customary for the surveyor to cut down the offending trees. But in property surveying, the property owner would be quite upset to find valuable trees destroyed just so the surveyor could establish a boundary line. So, prolonging a line past n obstacles. How? There are three methods for it: a right angle offset method, a random line method, and a triangulation method. So about first method. On this figure you can see technique of right angle offset method. Boundary line AE cannot be run because of the wooden area. The survey continues normally to point B, just clear of the wooden area. At point B, a right angle is turned and doubled, and point C is located a sufficient distance away from B. A right angle is turned and point C is located a sufficient distance away from B to provide a clear parallel line to the boundary line. The instrument is set at point C and sighted at B. Angle of 90 degrees is turned to locate point D. Point E is located on the boundary line using a right angle, and the offset distance used BC. The survey can then continue to F. If distance CD is measured, then the required boundary distance AF is AB plus CD plus EF. In figure, the next. Trees are scattered over the area, preventing the establishment of a right angle offset line. In this case, a random line, open traverse, is run by deflection angles through the scattering line. The distance AF is the sum of AB, EF, and the result of BE. The technique of right angle offsets has a larger potential for error because of the weakness associated with several shot sightening at the same time. However, this technique gives a simple and direct method for establishing intermediate point on the boundary line. So you already know three methods: prolonging a line past an obstacle by triangulation, right angle offset method, and a random line method. So thank you, and you know that for a civil engineer there is no such thing as a little mistake. Bye.